Hi, this project is real-time EV dashboard and ADAS warning system. It combines microcontroller STM32 and ADAS algorithms and Python graphical user interface. And I'll explain why this project is needed, how the system works, and implementation, and finally demonstrate it. Why smart EV dashboards matter? Because modern electric vehicles generate huge amounts of data. Drivers cannot monitor every sensor data individually. Missing important warnings can lead to accidents. Engineers also need a way to visualize all this during testing. So we came up with a solution that integrates everything into one dashboard. The STM32 continuously reads sensors, processes EV calculations, performs ADAS safety checks, and sends data to computer. Python receives the data and displays everything in real time. Okay. Next, system architecture. This is the brain of this project, and you can see the flow of this project. The sensors send the data to STM32 ADC pins, and this converts into digital values and sent to the EV logic and ADAS logic. And finally, this EV logic and ADAS logic calculate the distance and speed, torque, etc. and sends the data to the Python through UART communication and finally display the dashboard. There are nine phases. There are nine phases in this project. First, this is environmental setup. These nine phases will be explained in next coming slides. First is environmental setup and peripheral configuration, sensor integration, EV physics, and ADAS. Next is fault management, UART communication, and command shell and dashboard. And next is hardware and pin mappings. You can see the microcontroller communicates with peripheral devices or external devices through GPU thing. So pin configuration is essential. PA0 and PA1, PA2, PA3. These are four ADC pins and configured as ADC in the STM32 by DE. Okay, and where PA0 is for acceleration and PA1 is for brake and PA2 is for SOC and PA3 is for motor temperature. Next is about the hardware mapping, hardware specifications, where the main brain of this project is microcontroller node where STM32F103C86 is the one which we used here, and we have used the three ultrasonic sensors which measures obstacle distance, and we have used LEDs to provide visual alerts, and we have used potentiometers to which is used to simulate accelerator, brake, battery temperature. The programmer as a simulator simulates all these components. Is about the hardware and pin mappings, and next about the and environment setup. Softwares which we used are STM32 The STM32 is about the firmware development, and the programmable simulator is about the hardware simulation. Python is for dashboard, and Matplotlib and MySerial are libraries which are used for reward communication and visual plotting. Next, timer 1. You can see the STM32 peripheral design. Timer 1 is 10 milliseconds EV update, and timer 2 is for ultrasonic timing, and timer 3 is for sensor scheduling. And next, uh, ADC and EV physics. ADC means it converts analog voltage into digital values, where we have used digital values, where we have used a 12-bit ADC, 12-bit resolution of ADC, where PA0 is accelerator and PA1 is brake and PA2 is S-force and PA3 is motor temperature. And the next one is EV physics. Here the main intelligence begins. The throttle increases torque. Torque increases speed. High speed consumes battery. Braking activates a regenerative braking. Regeneration increases battery charge. This makes the dashboard behave like a real electric vehicle than simply displaying sensor values. ADAS engines. ADAS stands for Advanced Driver Assistance Systems, where there are forward collision warning, time to collision, blind spot detection, parking assistance mode, and overspeed safety advisory. Where forward collision warning is about the front obstacle, detects front obstacles, and time to collision predicts how soon a collision may happen. And blind spot detection warns about vehicles beside the car. And parking assistance activates at low speeds. And overspeed warning warns if speed exceeds safe limits. This improves the driver safety. The next is about the fault and alarm systems. Every fault has one bit. Examples: over temperature, low battery, and collision and communication failure. This explains alarm priorities. This explains alarm priorities. Level zero. Level zero is nothing but there is no level zero. Um, LEDs remains off. Buzzer is silent. I mean, no obstacles, no forward collision warning, and no time to collision like this. So then only alarm done. Level zero. Level alarm occurs. Alarm advisory when speed is exceeding the safe limits, then alarm advisory indicates triggers yellow LED. And alarm warning the when you can see here the yellow condition, then the distant collision warning is less than 50 centimeters and time to collision is less than 3 seconds. If any of the two conditions is satisfied, then the red LED or red LED may glow. Red LED glows, not may glow. Next is alarm critical. When the front obstacle distance is less than 20 centimeters and time to collision is less than 1.5 seconds, then the red LED glows and produces and indicates that level 3 alarm critical you are in danger. This is about the diagnostics and alarm system design. Next about the UART telemetry. UART transfers data between STM32 and Python. For every 100 milliseconds, STM32 sends speed, battery, torque, temperature, range, acceleration, brake, everything. Another packet contains front distance and the left blind spot left and blind spot right, time to collision and collision warning, blind spot detections, and alarm and faults. You can see from here for every 100 milliseconds it sends. The STM32 sends for every 100 milliseconds STM32 sends data to the Python. Here we use ASCII packets because it is easy to debug and easy to parse. Python reads these packets and updates the dashboard. And next is about the command shell. We give some specific commands such that like this we can see the command interface syntax like should be like mod echo mode or normal mode or smart mode. If this mode is set according to that the range the speed is set in we can see in the dashboard. If we set SOC set above 100 degree above 100, like not this one. If you see some okay, if you set SOC set to 0 degree Celsius, zero, straight up as zero, then the torque is zero because we have set like that. And next is speed. The speed is greater than 120 kilometer per hour. If we set the speed which is greater than the safer limits which is mentioned in the code, then automatically the alarm signal like I have shown here that when the speed is greater than 120 kilometer alarm this should appear in my dashboard like this. If the com if the for this commands if the output is correct, if we see the respective outputs, then we are sure that we this is good. Next, this is useful for testing, debugging, validating alarms and without changing hardware. Next is for Python dashboard, real-time dashboard. Now speedometer dial. This speedometer dial displays current speed. Next battery bar shows battery percentage. Next history graph shows previous speed values and ADAS speed shows obstacles and blind spots. And metrics panel this displays temperature, torque, temperature, torque, faults, alarms, mentions, alarms. And Python uses UART data, extracts values using regular expressions, and updates matplotlib every 100 milliseconds. Next, end-to-end system data journey. First, sensor acquisition. Next, stage 2 is processing, and stage 3 is visualization. And this is a complete real-time. This is a complete real-time pipeline. Next, finally, we achieve the real-time speed, real-time dashboard with smooth speed updates, battery monitoring, collision detection, blind spot detection, and over temperature control, and everything like this. The complete communication chain worked successfully in simulation. Finally, thank you. This project helped me understand embedded system, real-time communication, sensors integration, UART protocols, and dashboards visualization. It gave me practical experience in developing in automotive style and embedded applications. Thank you for your time. I would be happy to answer uh, any questions if anyone asked in my interviews, or if a teacher asks. I'm very happy to answer to this. And finally, I will demonstrate how this worked actually. This is my STM32 cube ID where I create a new project, new STM32 project. After this, we after this we and again we go for source file and header file. We create source file and header file. The source file is with .c and header file is with .h file. We see that this is the main. Before this, we have to do one thing, that we have to configure, like whenever STM32 ID is opened, the first thing it opens is this one. This is IO configuration. You can see here. Yes. This is, you can see this is the STM32, our STM of our blue pill. You can see here PA0, PA0, PA1, PA2, PA3. These are configured as ADC pins, and this PA9, PA10 is configured as transmitter receiver pins, and PB0, PB1, PB2, PB10, PB11. These are configured as GPIO pins, and PB um, 8, 9. You can see everything here which is configured here. We can set the timers here. Timer 1. Here we have set the timer as internal clock as an update interrupt, and timer 2 is just for ultrasonic sensor. Timer 3 is set as global interrupt. This is the main. Whenever we configure this, when we configure this, and we have set the I have to set the clock configuration initial. First, we have to set this. We have to put to from initially it is here HSI. Then we have to shift to HSC. We have to make it to 72 megahertz. After this, we will have one main.c generated code which is generated by STM32 software itself. Many of the part is generated by software itself. Later we have to integrate everything. Like this is the EV logic. You can see here. This is the EV logic here. This is the EV part, and this is about the ADAS part. ADAS part. You can see the collision warnings here. Collision warning to when to turn on the LEDs. You can see when whenever the collision warning is greater than 0, we have make it to we have made the GPP pin to set. When the collision one when the blind spot left is equal to 1, we have set pin 9. If it is not equal, then directly it goes to reset. Means it is in off state. You can see from here. And next is this is about the fault. If we see, if we can see here that whenever motor temperature is greater than EV motor, we have mentioned, we have Yeah, header files. In header files, we have mentioned that this is the threshold values like maximum motor temperature. Like you can see that maximum motor temperature it can withstand it. The vehicle can withstand is 90 degrees Celsius. So this is mentioned here. This is 90 degrees Celsius because we have mentioned this for common dot h. If the water temperature is crossing this directly, new flag is set to fault underscore ot on over temperature. Then if the new flag is set to this one, then finally this condition is failed and finally directly it goes to this and finally sorry finally it goes to this condition is passed and finally goes to this and sets the pin 11 as set. And the next is you can see ultrasonic. Here, this is the main, this is the core code where we find the distance, measure the distance. We have the logic here for finding the distance. You can see we have set the timer 2 here, timer 2, which has to measure at least for 10 microseconds to trigger the pin. Um, whenever it receives, whenever it receives a trigger pin at least 10 whenever trigger pin receives at least 10 microseconds of high, then directly the this one is calculated and distance is calculated with this formula and time into sound by 2 because it travels 2 times, so we divide it by 2. And finally the main dot c we will integrate every dot, I mean header files here. And finally you can see that here sensor flag for which we have set for ultrasonic sensor we have set timer 3 for 100 milliseconds it should have interpreted the generated. For 10 milliseconds the EV should be updated. For example, if here when EV division is greater than or equal to 10, that means for every 100 milliseconds the both gets updated and sends the data to the Python dashboard through UART communication. And after this you can see, oh wait a minute, here we have main.c. First we have to build the project here, build the project. Yes, you can see the build finished. Again I'll build the project, build finished. And next we have to go for project and properties and settings, convert to manual file. Apply if you apply and close it, it converts a binary file. Next this part, this STM32 QID part is over. Next is finally we have the PA simulator lab. This one you can see here. From here we load the pin. It asks a load pin which pin should be loaded. We have this is the bin which is generated. We load this, and after loading, first we have before loading we have to set the space parts. The space parts part will be looking like this. This is space parts log or block. By setting properties, by pressing properties, we configure these pins. This is acceleration. This is brake, and we can wait a minute. Text box properties, acceleration underscore pedal, comma brake, comma SOC, comma temp. Okay, this is set. This is temporary. This is SOC. PA1 is brake and PA0 is acceleration pedal. We can see here the trigger pin and lock pin PB0, PB1, which is configured. You can here we have configured as P0 configuration. You can see here PB0, PB1 output and input we have configured. So in the same way, the trigger pin should be the output and echo pin should be the input. for three ultrasonic. This is for front, and this is for left, this is for right. You can see the this is the IO virtual term. By pressing this, we get this IO virtual term. This is, you can see here that PB8, PB9, PB10, PB11. These are the fault indicator LEDs. You can see after loading the pin, we may see this one. You can see here. You can see here. I'll just clear it. You can see here the speed is 31.9, state depth is 94.2, the range is 3141, acceleration 32, brake 0. So if you see that if I change this distance less than 30 centimeters, okay, the LED glows. This one is also glowed because front is less than 19 centimeters. If I set this one to the less than 20, this should be glown. In the same way, this is also glown when less than 30 centimeters. You can see here, and if and you can see the torque. You can see the torque is zero here. Whenever uh, whenever no LED glows, the torque is, you can see the torque is appeared here. See, torque is changed for 48 in the same way. So the speed, you can see the acceleration is 32, the brake is 0. If I increase this, you can see, you should be able to see the difference from 32. You have to see the difference. Wait a minute, you can see some 32 to 77. The same way the brake brake is 33. Okay, next, and this part is over. Next is Python part. In this Python, we have the important libraries are serial for serial communication, threading for serial communication, and plotting. We are performing two operations at a time. So this library, and matplotlib for visualization. This threading runs UART communication in a separate thread. Without threading, reading serial data in the dashboard cannot happen simultaneously. One thread simultaneously receives data while the main thread updates the dashboard. Okay, this is one of the most important concepts. Next is read. This is about the regular expressions. Extract values from this library extracts the values from UART packets. Next is like if we get a packet like this, speed, SOC like this, reject separates speed, SOC, torque automatically. Next, matplotlib dot pyplot as PLT. This creates a speedometer, battery gauge, graphs, ADAS view like this, and NumPy for demo. Okay, this is a dictionary. Next, parse line. You can see here the parse line. The, you can see the parse line. This is one of the most important functions where this converts the UART text into usable values. STM32 sends like they sends like this. Yes, like this. Python cannot directly use this string. So what it does is it just extracts the numbers, the float values, then updates the state, then updates this one. Okay, next another UART line also same the same way this works. Next, serial read thread. This one, serial read thread. Serial read thread. You can see here the comment. Open comp this opens the com port and waits for STM32 data. Step 3 reads one line and call parse line repeats forever and explain. Um, If UART blocks, then dashboard freezes. Threading prevents that. Next, you can see the demo mode. Even if no connection, just to see the dashboard how it looks, this is used. This NP is nothing but the NumPy library. From this line, the NumPy library we use this sine, cosine functions. And overall, the STM32 sensors sends the data to UART communication through serial reader thread. You can see here serial reader thread. From this, it passes the line and updates the state dictionary and dashboard functions. And finally, we get the speedometer, battery, ADAS, graphs, and information level. Okay, you can see here. I'm just going to run this. What happened? You can see here. It showed it connected. It should be get updated. So what I do is I just press this. Okay, you can see here the 30 speed is 30. The speed is 30. State of charge is 100. You can see here. You see the torque is minus 18. I have to change this. Wait a minute. I've changed it. Now you can see that torque is 150 nanometers. Sorry, Newton meters. You can see the same here. You can see the parallelly. I'm going to give situations where forward collision warning is going to occur. So let's just see here. You can see that forward collision warning is the red LED glow. You can see the same here too. You can see the same here too. It is showing alarm critical. Just to stop the our torque is also zero. The same way as produced in virtual term. And again, now I'm going to change this, and now I'm going to decrease this. Now you can see the green LED glowed. You can see. So in the same way, the left side vehicle should come. Um, this you can see the blend. Left side vehicle is also very near, so the torque is, yeah. So the green LED glowed. Okay. In the same way, the right side, the blue LED glowed. You can see it updates. Wait a minute. I can see here. You can see here that. So if I change, you can see that if I change the motor temperature 0 to greater than, you can see here the motor temperature is 120 degrees Celsius. According to this, the torque should be 0 because it is crossing the threshold. So in the same way, the torque should be equal to 0 here. The temperature is 120 degrees Celsius here. You can see, you can observe it perfectly here. And the fault is 1. Okay, everything is working perfectly. And I'm reducing it. I'm reducing the state of charge now. You can see the range is decreasing 3300 to 300 kilometers. You can see here, you can see 3294. It is decreasing because the state of charge is decreasing, the range is also decreasing. There, the algorithm is written in such a way that if the state of charge is decreasing, the range should also decrease. Okay, if I improve the brake and decrease the acceleration, let's see what happens. The brake is changed to 63, the torque is changed to minus 35. That means it is slowing down. You can easily understand from this. Okay, everything. is perfect. And finally, this is about the EV dashboard, real-time EV dashboard, and ADAS one ADAS system. Thank you very much. Thank you very much for listening. This is a wonderful experience to talk about my project. Thank you. Thank you very much.